So in the previous lecture, we have talked regarding the law of large number. With the help of Markov's inequality and Chebyshev's inequality, we are able to prove what is the law of large number. In this lecture, we'll see little bit of geometry of high dimensional space. And the important property of the high dimension object is the most of their volume is near the surface. That we are going to prove here. So for that, let us consider any object A in RD. As I already defined, what is RD is the d-dimensional space, and I'm considering any object in RD. Now let us shrink this object by a small amount epsilon to produce a new object, that is 1 minus epsilon into A. So as per the definition, what is this? It is a set of all points where 1 minus epsilon into x, where x is in A. So what I'm telling you, suppose you have one sphere in d-dimensional space. This is the sphere in d-dimensional space. Let us consider. And its radius of this sphere I'm considering as 1. Now let us consider this is my object A. We'll shrink this object by small amount of epsilon. Okay. So if you shrink this object by smaller amount of epsilon, then the situation is like this. So this distance is epsilon, very small. So the radius of this one will be 1 minus epsilon. So exactly is denoted 1 minus epsilon into A. Now it is not necessary that it is always a sphere. This object is any object in three-dimensional space. Let's say it is a cube in three-dimensional space. Okay, this is a cube in 3 dimensions. But if you can consider a cube in d-dimensional also, the same concept you can generalize for that. And if you shrink this object by this much amount, so every edge will be shrink like this. Okay, and you will have inside another cube. So same way you can just visualize what will be, one object is given to us and we are shrinking a small amount, that is the epsilon amount, to produce a new object, that is this 1 minus epsilon into A.
Excuse me, sir.
Yes.
Sir, someone wants to join.
Yes, sir.
Okay, now what will be the volume of this new object? So the volume of 1 minus epsilon into A is equal to, you just see that. Suppose it is a three-dimensional space, and if it is a cube and it is a side is, let's say, 2, then what will be the volume of the yellow one? Yellow cube. What will be the volume of a cube? Its one side is 2. All of them is 2 because I am talking about cube, not a rectangular cube. What will be the volume of a cube? Yes, guys, you don't know how to calculate the volume of the cube? Is my voice is
Sir, L into B into H.
huh?
Sir, it is side cube. Side cube. A cube.
Sorry. A cube, A cube.
A
Side
cube. So it is
cube.
so it is, I said it is a 2. So it is a 2 cube of yellow one. Now this red one cube which we have here, we have shrink that one by epsilon amount. Okay, so each side is a smaller by epsilon amount. Okay, so how much, what is the volume of that cube? So
2 minus epsilon cube.
2 minus epsilon cube. Okay. So in general, if the volume, for example, here if we can talk about the sphere, if the radius is 1, then it is pi 4 by 3 pi r cube is the volume of a sphere. Okay. And r is 1. So it is 4 by 3 pi is the volume of this red one. If I want to calculate for yellow one, that is 4 by 3 pi 1 minus epsilon cube will be there. So it is actually 1 minus epsilon cube into 4 by 3 pi, where this one is the volume of the red one. So in general, the volume of 1 minus epsilon into A will be 1 minus epsilon power D into volume of A you will have. Why this is happening? The portion of A into infinite cubes, suppose you have a object, you can divide that into the infinite cubes, and then 1 minus epsilon A is the union of set of all cubes contained by shrinking the amount cube in A by factor 1 minus epsilon. Now when we shrink each side D of the d-dimensional cube by factor f, then the volume will be shrink of f raised to d. Okay, so that's why this is the things we can have. Now there is one identity, or I can say inequality, which you have probably studied in your undergraduates. But if not, then I will try to prove that one here. That is, this is the fact, it is always true. I can say the fact is, for any x positive, 1 minus x is always less than or equal to e power minus x. Now to see this, why I want to use this one quantity here. So that's why it's required. To see this one, you just define a function f of x is equal to 1 minus x minus e power minus x. You just define this function. And if I want to show that this function is, because I want to prove that this 1 minus x is less than or equal to, sorry, 1 minus x is less than e power minus x is negative. That I need to prove now. This is our objective. Because I want to prove this one, so I have to prove this. So for that, I'll just take the derivative of this function. A derivative of this function will give me minus 1. The derivative of 1 is 0. Derivative of x is minus 1. A derivative of e power minus x is plus e power minus x. And you can just see that this is minus 1 plus 1 upon e power x, and this will be the minus e power x plus 1 upon e power x. So what you can say about this quantity, whether it is a positive quantity or negative quantity? 1 minus e power x.
Positive.
Positive.
Negative, sorry.
Exponential function is the graph of the exponential function start from 1 and it goes increasing if x is positive. Okay. So this is the graph of the function, exponential function. So this is a negative quantity. So you have any results in your calculus which you have studied that if f dash is negative, then what you can say about the function, whether it is increasing function or decreasing function. And f is a decreasing function. This is very fundamental concept which is already covered in 12th standard also. So if f is decreasing function, then x is greater than 0 will implies that f of x will be less than f of 0. Okay, because it is a decreasing, so this inequality will be changed. So that will implies f of x is this function, that is 1 minus x minus e power x is less than or equal to f of 0. If you substitute 0 here, then you will say it is 1 minus 0 minus e power 0, which is also 1. So 1 minus 1 is there, so that gives me 0. So it will prove this concept, that is 1 minus x is less than or equal to e power minus x. This is always true. And if I use this concept here, this inequality here, that means the volume of 1 minus epsilon into A is equal to this much. We'll use that one. So the volume of 1 minus epsilon power d into A, 1 minus epsilon to A is equal to 1 minus epsilon power d into a volume of A. But this quantity is less than or equal to e power minus epsilon raised to d. Due to this one, 1 minus x is less than or equal to e power minus x. So the 1 minus epsilon, instead of x we have epsilon here. That is less than or equal to e power minus x and whole power d into volume of A. So therefore what we got is volume of 1 minus epsilon into A upon volume of A is less than or equal to e power minus epsilon into d. Now fixing epsilon, that means epsilon is fixed, and letting d tends to infinity. What will happen to this inequality? What will happen to this e power minus epsilon raised to d? Then what will happen? Tell me. We get what we will get. What is d tends to infinity? What will be this quantity is tending to?
Infinity.
Infinity. How many of you are saying it is infinity?
It's 0.
Okay. E power minus epsilon raised to d. So this will tends to 0 as d tends to infinity. Why? Because e power x is tends to infinity as x tends to infinity. This is e power minus x. So it is 1 upon infinity things. So that's why this will tends to 0 as d tends to infinity. What does it mean? Can somebody tell me what this means? The volume, nearly all the volume of A must be in the portion of A that does not belong to the region 1 minus epsilon into A. What does that mean? That all the volume lies in between these two things. That means what we have proved here is in high dimension, the most of the volume is near to its surface. The same concept you can see for unit ball also. Let S denote the unit ball in d dimension. When I say unit ball in d dimension, that means it is a sphere. You can see sphere in 3 dimension. Then you can just try to observe the same concept for 4 dimension, 5 dimension, and in general d-dimensional space. That is the set of all points with the distance 1 from the origin. So if I can say in the set notation, that means set of all x1, x2 up to xn, it is in Rd, such that x1 square plus x2 square plus x, this is d-dimensional space, so that's why I should write d here. This is d, so it is d power square x d power square is less than or equal to 1. This is a closed unit sphere. An immediate application of the above observation that we have discussed just now is the least portion of the fraction 1 minus e power epsilon d fraction of the unit ball is concentrated in this s minus 1 minus epsilon s, namely a small annulus of with epsilon at the boundary. That means the annulus means the area between the two spheres, that is known as annulus. If this is the one sphere and this is the another sphere, then the area between them, it is known as annulus. That is exactly this area I'm talking. The whole is S, the bigger one is S, and this is epsilon. So that minus this one. So whole minus the middle portion, that will left with this one. Okay. So it says that in the small annulus with width epsilon at the boundary. In particular, the most of the volume of d-dimensional unit ball is contained in annulus of width big O of 1 upon d near the boundary. If the ball is of radius r, so here I have considered the radius is 1. If the ball is of radius r, then the annulus width will be r upon d, and its d tends to infinity. What is the big O? The fx is equal to big O of g of x, means that fx is less than or equal to some constant into g of x. So what is saying that radius of this annulus, that is epsilon, is equal to this much. What does that mean is epsilon is less than or equal to C times 1 upon D. And if D is tending to infinity, then this epsilon is, so that is the portion, the volume of that portion that is talking about. So that is the first observation that we can make out here, is the most of the volume near the surface in high dimensional space. Everything is concentrated near the surfaces.